The natural exponential function. Section 4.2 deals with the natural exponential function. Okay. Any positive number can be used as a base for an exponential function. The focus of this particular unit, or this chapter, excuse me, the section in our chapter, is to talk about the special base of e, which is convenient for applications involving calculus. Now, what it looks like is e to the x power. Okay. Now, I know your whole life that people have told you that E is a letter. Well, that's because it's true, but it's also used to represent a number. It's a very specific number. It's even stored in your calculator, okay? Um, if you use a calculator like mine, there's actually a button for it right here. If you use an 84, there's also an E button on your calculator. It's stored in the calculator, obviously up to a certain digit. Or decimal, excuse me, but it's definitely a very specific number. It starts with 2.71828 and goes on from there. It's an irrational number. It cannot be written as a fraction, okay? And it's a number that's very, very important in a lot of mathematical ideas, okay? The number e is defined by the value, as the value that 1 plus 1 over n to the n power approaches as n becomes large. In calculus, this idea is made more precise through the concept of a limit. Okay, we don't talk about limits in Algebra 2 very often, but E is one of the places where we can kind of start to talk about it. Okay, the table shows the value of the expression 1 plus 1 over n to the n power for increasingly large values of n. It appears that, rounded to 5 decimal places, E is going to be approximately equal to 2.71828. Okay, so you can look down at this table if you want, or you can just know that it is approximately 2.71828 as n gets very large. Okay. The natural exponential function is the exponential function f of x equals e to the x, where e is our base. Okay. It's often referred to as the exponential function, natural exponential function. Okay. Whoa. Since 2 is less than e is less than 3, we know that the graph of the natural exponential function lies between the graphs of y equals 2 to the x and y equals 3 to the x. Okay, y equals 3 to the x is this one up here, y equals 2 to the x is this one up here, and y e to the x is that one right there. Okay. Now I showed you on my calculator, here's an example of on an 84, to see how the e is right there, right above the natural log key. Okay, or ln. You may not know what ln means quite yet, but that's our natural log key. Okay, we will use this e key in our next example. Okay, now just for the record, making sure because we talk about this sometimes, there is an e key on our phone. Okay, right here. Remember, we talked about how you can take the calculator on your phone and turn it sideways. There is an e button on your phone calculator if you need to use that as well. Okay. Of course, not on a test or anything like that, but if you're working on your homework and you don't quite have your calculator right with you, you do have it available on your phone, okay? So if we're evaluating things like e to the third power, okay, we can just say e to the third power. Now it's mad. The third power of e, that's what I needed to do, okay? So e to the third power then would be, let's round it to 5 decimal places like it asks. It would be 20.08554, because that next one's a 6, so that one's got to round up. Okay. So on your calculator, obviously you would press E and then the raise button and then negative 0.53. Since I'm using my phone, I'm going to have to say 0.53 negative, and that's an exponent of the E. Okay, but I also have the 2 times that, so I need to now multiply it by 2. And since I'm still rounding to 5 decimal places, let's say 1.1772. 1, 2, 3, 4, 5. That's what I'm rounding to, so I need to look at the next one, a 9, so that will bring that one up to a 1. Okay? And last but not least, e to the 4.8 power. So 4.8 raised to the e power. Again, 5 decimal places. That's going to take me 121.510 for going to the fifth, 1, 2, 3, 4, 5. So I look at the sixth, that's higher than 5. I'm going to move that to a 2. Okay? Does that make sense? How to evaluate expressions with an E in it? Okay? Sketch the graph of each function. So we start with f of x equals e to the x. That's our parent right there. And we need to use our transformation rules on this particular function. Okay? When I use my transformation rules on this particular function, I realize that this is inside my function. And when it's inside my function, I know it's going to move left or right. It's a horizontal shift, backwards of what I think. Okay? This is plus 3, so I know it's going to go left 3. 1, 2, 3. Just moving that point because that's the easiest one to move. Okay? And then I know that's outside of the function. So that's going to cause a vertical change. And I know it's plus 1, so it's going to move exactly where I think it should be. So it should go right there. Okay? So my new function will look something like that. Now when I look at my domain, I know my domain of exponential functions is going to be negative infinity to positive infinity, all real numbers, because it goes all the way left and all the way right. Even when it looks like it's just going straight up, I also know it's going to the right as well. As far as my range goes, I know that it's going all the way to 1, but not crossing 1 and not going below 1. So that's going to be 1 to infinity, not including 1, because remember it doesn't quite get there. And my asymptote is going to be right there at that y equals 1. Okay? Infectious diseases are often examples used for exponential functions because they absolutely follow an exponential form. It's gotten a little bit more close to home in the last couple months, well, last couple years, I guess I should say, because of our exciting activities that have gone on in our world. But we're just saying it's an infectious disease, not any one in particular, just a general infectious disease. Okay, so an infectious disease begins to spread in a small city of population 10,000. After 10 days, the number of persons who have succumbed to the virus is modeled by this function. So in this particular example, this is the function that we are given to use. Okay, how many infected people are there initially at t equals 0? Okay, well, if t equals 0, 0 times negative 0.95 is 0. And I know anything to the 0 power is 1. So this value right here is a 1. So what I end up with is 10,000 divided by 5 plus 1245, which is 1250. So 10,000 divided by 1250 is 8. So what does that mean? 8 what? Well, how many infected people are there initially? Well, 8 people. So at the beginning of this infectious disease situation, 8 people were infected. And after t days, we could use this model to figure out how many people are infected now. Okay? Find the number of infected people after 1 day, 2 days, and 5 days. Well, after 1 day, t would be 1. Okay? So I would use my calculator. I put it where hopefully you can see it. Turn it on. Hopefully it will come on. Okay, it'll take a minute. So I'll go ahead and fill everything in that I know. 10,000 over 5 plus 1.2, well, not 1.1 comma 2, 4, 5, e to the negative 0.97 times 1. Okay, I'll put that in just a second. As soon as my calculator comes on, I'll go ahead and write down the rest of these. 10,000, 5 plus 1,245 e to the negative 0.97 times 2. And then day 5, 5 days equals 10,000 divided by 5 plus 1 comma 245 e to the negative 0.97 times 5, okay? Okay, so we're going to say a fraction, 10,000, 1 plus 1245 e raised to the negative 0.97 times 1 power. Now, we're trying to find number of infected people. So this is 20.9662. So hopefully you can see that that's going to actually be 21 people, because we don't want to put 20.96 because that implies there's 0.96 of a person. You know what I'm saying? Okay, so 21 people. So after one day, we started with 8 people sick. After one day, now we have 21 people sick. Okay, well, what if it is a 2? After 2 days? Well, after 2 days, we have 54 people sick. And then after 5 days, we have, oh geez Louise, 678 people sick. Now that seems crazy, right? Except this is an exponential function, so it's not getting faster linearly, it's not getting faster or anything like that, it's getting faster exponentially. So that's why when people say things like it's exponentially more expensive or it's exponentially longer, it means it's a lot longer, a lot faster. It's a lot more expensive, a lot faster, okay? Exponentially, okay? Graph the function v and describe its behavior, okay? So let me graph this. I'm going to add a page that is a, whoops, add a page that's a graph. So I'm going to say, whoops, 10,000. 5 plus 1245 e raised to the negative 0.97 x power. Okay. Now, this is what they want me to change my window to. Let me scoot over here to the side so you can see it. Kind of. I'm going to go to my menu, my window. My window settings are going to go from 0 to 12. And from 0 to 3,000, counting by thousands. I'm going to zoom in on it just so you can see it a little bit better. Okay, so this is what it looks like when you zoom out and look at this function. Okay, notice what happens. It's increasing really quickly and then it flattens out. Why do you think it flattens out right there? Why do you think it flattens out around 2,000 people? Well, because at some point, I mean, it doesn't exactly flatten. It's still increasing, but at some point, things change because you kind of run out of people to get sick, right? Okay. This graph. Well, let me zoom back out. Give me just a second. This graph is called a logistics curve or a logistics growth model. Curves like it occur frequently in the study of population growth. Okay. Now, we were just talking about an infectious disease problem, so obviously it occurs there as well. Okay, but it occurs often when you're studying about population growth, a graph that looks like this. Okay. Now, with compound interest, we saw that the interest paid increases as the number of compounding periods increase. Let's see what happens as n increases indefinitely. Okay. We can talk about monthly, then weekly, then daily, but what happens if it's compounded continuously? Well, if our interest is compounded continuously, we use a completely different formula. Okay, the formula we use is specifically for compounded interest that's being compounded continuously. And it says A of t equals PE, which is that natural base that we were talking about earlier, raised to the RT power. A of t is the amount after t years, so it's the amount you end with. Principal is the amount you start with. E is that number in our calculator that we've been talking about. R is the interest rate per year, and T is the number of years. Okay? So find the amount after 3 years if $1,000 is invested at an interest rate of 12% per year, compounded continuously. Okay? So we want to, what we end with is what we're trying to find. So A of T equals 1,000, which is what we start with, E raised to the RT power. So R is our rate. So it's 12%, so it goes in as 0.12 times T, which is 3. Okay? Now that's something we put straight in the calculator, 1,000 times E raised to the 0.12 times 3. And when I do that, I get $1,433.33. Okay? Put a dollar sign there. That's our answering our question that's being asked, find the amount. Okay? Now, let's do another example. Okay? 1, 2, 3, 4 possibilities here. Okay? We're going to have to use a combination of the compound interest formula that we used last time, as well as the one we just learned with compounded continuously. Okay? In this case, we are starting with $300 at 2.5% interest rate per year. We want to find the amount invested, the amount that we end with after 11 years. Okay? 4 different ways: annually, semi-annually, quarterly, and continuously. Okay? I want you to see what's going on here. So for these first couple formulas, let me remind you that A of t, or not formulas, the first couple equations equals P times 1 plus the rate, R, over n raised to the nt power. Okay, so 1 plus r over n raised to the nt power. So in this case, we start with, well, A of t is what we're trying to find. We start with $300, 1 plus the interest rate, which is 2.5%. We've got to take that to its decimal, which is 0.025, over the number of times per year it's compounded. Specifically, this time is annually, so that's a 1, raised to the 1 times t power, which is 11. Okay? So I'm going to put that straight into my calculator, push all these numbers in, and what I'm going to end up with is $393.63. Okay? Now semi-annually, A of t equals 300, 1 plus 0.025, but this time it's going to be divided by 2, raised to the 2 times 11 power. Okay? Annually, my n was 1. Semi-annually, my n is 2. Now, when I change from annually to semi-annually, my amount that I end with is $394.29. So not a huge difference, but still a difference. Okay? Quarterly, what if I change to quarterly? A of t equals 300, 1 plus 0.025 divided by quarterly, which would be 4, raised to the 4 times 11 power. Okay? So when I put this in my calculator, I get $394.62. Okay? Still not a huge amount of difference, but it's still a difference, right? It's still an increase depending on how many times per year that it is compounded. So now what if I compound it continuously? Okay, compounded continuously takes a different formula. That's the one we just talked about. Okay, so I start with 300, e raised to the 0.025 times 11. Multiply the rate times the time here in the exponent. Okay, now when I do that, I get $394.96. Okay, So the more times per year that I compound my money, the greater my end yield is of my investment. Okay? Animal populations are not capable of unrestricted growth because of the limited habitat and food supplies. Under such conditions, the population follows a logistics growth model. And that model is given for us right here. Okay? P of t equals d over 1 plus k e raised to the negative ct power. Okay? Now, please understand when we're given situations like this, because we are not animal population experts, or where I'm not. Maybe you guys are, but I'm not. Okay? What it does is it doesn't define everything for us. We don't know exactly what these are, but it does tell us that they are positive constraints, and it does give us values for them, so we're not having to find stuff that we don't necessarily understand. Okay? We're basically just saying, can we figure this out? Can we figure these exponential functions out? Okay? So let's see what goes where and put everything in. P of t equals d, which is given right here as 1,000. So 1,000 is what is in my numerator, divided by 1 plus k, and k is 9. So 9e raised to the negative c times t power. Well, I've got my negative right there. C is 0.2 times t, which is measured in years. Okay, and when the fish were introduced, our t was 0. So we're putting t as a 0. Okay, so when I put that into my calculator, let's just go ahead and do that together this time. Oops. I need a fraction, so I need 1,000. 1 plus 9, oops, e raised to the negative 0.2 times 0 power. And that gives us 100. So what does that mean? Well, when I introduce the time here, it says t is 0. How many fish were originally put in the pond? Well, that's when t was 0. So we know that 100 fish were originally put into the pond. Okay? One last example here. Okay? Still part of the same kind of problem, but this time we are finding the population after 10, 20, and 30 years. So we're using the same formula from before, right here, but instead of putting in a 0, we're putting in first a 10, and then a 20, and then a 30. Okay? So right here, I'm putting in a 10. When I put in 10, I get 450, oh, you can't see that, sorry, 451, okay? 451 fish, okay? Like I said, we're using the same general formula right here before, and said this time instead of 0 for t, we put in a 10 for t. This time instead of a 10 for t, we are putting in a 20 for t. So this time we have 858 fish. And this time instead of 20 years, we are putting 30 years. And this time there are 978 fish. Okay? Now, evaluate PT for large values of t. What value of the population does t approach? Sorry, what's the value of the population approach as t goes into infinity? Well, we use 10, 20, and 30. What if I put like 100 instead? Oh, it tells me exactly 1,000. Well, I know that's not exactly true. It's probably just rounded. Let's go down a little bit from there and see what happens. What if I put 50? So 50 is 999. Oh, you know what I can do? Let me real quick change my document settings. I know you don't have to do this because yours doesn't automatically round for you. Mine does. So I'm going to change it to flip 12 and see what happens there. Go back up to here when I plugged in 100. Okay, so it's not exactly 1,000, it had actually rounded. Okay, 50 is 999.592. 100 is 999.99998145. I don't know how much further we can go up before it just tells me 100 or 1,000 again. What if I do 200? See, 200 is already telling me 1,000 again, but that's also telling me what the population is approaching as T is getting bigger. Okay, my population is approaching 1,000, and if we look at the graph, we can tell that that's where it's flattening out right there. Okay, does that make sense?